So am I audible? Okay, so thank you. So so today I have planned the lecture on Markov models. So this was not the plan. Actually, I wanted to start optimization, but what I have planned is in today's lecture we'll cover Markov models, hidden Markov models. We'll see its application, and then we'll close. So if it is not of 2 hours today, then we'll close earlier, and then we'll start a fresh optimization from the next class. Okay. So this is the plan. And yeah, so I have already told you the content for today's lecture or session maybe. Okay, so what we are seeing is we have seen Bayesian networks where we are saying that there can be multiple states and each state can have some child node where it depends. So it affects the probability of the child node. So a node can the probability of the random variable taking a value is dependent upon the parent node. Now what we are talking about is bringing time into picture. So at one time point, we may be at a state which is represented by a random variable x naught. So x naught can take multiple values. And we say that this is a time point. Suppose we start at time point 0. And at time point 1, this state changes to x1. So x1 is a random variable which can take any value, whichever in the range it can take. And this occurs at time point 1. Okay, so these kind of models we'll see where there is some kind of flow in time. Okay, forward flow in time. The goal is to build a model that can predict future events based on the present observation. So it is not only just future events. Markov models can be, so Markov model can not only be used in terms of time, but it can also be used in relationship with one word to the other. So for example, if we're talking about natural language processing, so we can have a word and the next word, and we can say that this word is dependent upon the previous word and so on and so forth. So this type of models can also be built by Markov models. All right. So what is a Markov property? So Markov property says that the future state, so this is the current state and the future state. So the probability of random, so the distribution of random variable x1, so the probability, the values that x1 can take is dependent upon the previous state, and it can be finite number of previous states. Okay, so in the last class there was I got confused in finite number of previous states and single state, so we'll talk about that. But the idea is a given state can only depend upon some number of previous states and not infinite number of previous state. That is the main idea. Okay, so if you're talking about a state x1, it only depends upon some number of previous states. Okay, why are we making this assumption? You see, this can simplify our model. You see, if you are saying that the probability of x1 taking a value a depends upon all previous states, then you have to condition on all previous states. So suppose it is x0, x1, and dot dot dot. A lot of random variables are there, lot of states are there. Then what you have to do is you have to say probability of xn given each of these states. You have to say, you have to condition. So x naught took suppose a1 a naught, and x1 took a1, and so on and so forth. So for each of those states you have to condition, and obtaining these kind of probabilities becomes difficult as more and more conditions you incorporate in the distribution. So we make assumptions that there are some finite states on which the probability depends. So what happen is, so if I say this finite number is 1, then the probability xn given x naught is equals to so I should write like this: probability xn is equals to xn given x naught is equals to x naught, comma x1 is equals to x1, comma x2 is equals to x2, comma dot 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 xn minus 1 is equals to xn minus 1. This will be equal to, so if I say it depends upon the previous state only, then this probability becomes probability xn is equals to xn given xn minus 1 is equals to xn minus 1. So it is not dependent upon what the other variables previous to the previous state is taking. So it is independent of these random variables. And in such cases, obtaining such kind of probabilities and analyzing these kind of models become easier for us. That is why we are making this assumption of Markov assumption. Okay. So these are not particularly real world examples, but to analyze those examples, we are making this assumption. So for example, weather predictions. So we are assuming that today's weather is only dependent upon the past day's weather, so, or the past 2 days weather, or so on and so forth. Okay, so in general, it is true. So you cannot say that today's weather is dependent upon the last 1 year's weather. That is not true. So it may be dependent upon 2 3 day previous 2 3 days, or 4 5 days, or a month, maximum a month. Okay, so these kind of assumptions are not actually in real life, but they closely approximates to real life, and those approximations help us to reduce the complexity of the model. Okay, so reduce the complexity of the model, provide a manageable approximation for many practical problems. So we are trying to approximate. So you see there are two ends. Either you can have a very accurate model, but it will take a lot of time, or you can reduce the accuracy, which will take less amount of time. So there is a trade-off. So over here we are agreeing to make that trade-off. We are saying, okay, we will have some approximation in our model, provided it is less complex. So it is actually less complex and the approximation decreases. Okay. So what is a Markov chain? So over here, a Markov chain is a sequence of random variables. So first is x0, x1, x2, dot, 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 xn. It is a sequence of random variables where each random variable depend upon the previous one. So over here, I'm saying just the previous one. So before explaining a little bit further for this topic, I would go on to say types of Markov models. So there can be multiple types of Markov models, but I am classifying based on how many states the current state depend upon. So first is first order Markov model. So in this case, the current state depends only on the immediately preceding state. So xn will only be dependent on xn minus 1. Okay, and no other state it is dependent upon. So there is some kind of memorylessness. So previous to this, what happened will not govern the probability of xn. So there is some kind of memoryless property. Okay, mathematically I have written that probability earlier. So it says probability of xn plus 1 given xn to x1 is only equal to probability xn plus 1 given xn. So all these other random variables does not influence the probability of xn plus 1. So example we have already taken. Higher order Markov models, when we say it not just depend upon the immediately preceding state. So it can have 2 states or 3 states and so on and so forth. So what happens is, so suppose it depends upon the previous 2 states, then this probability, okay, I have not written this correctly. So it would have been xn comma xn minus 1 comma xn minus 2 comma dot 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 x0. So this would have been like this. Okay, so over here there is one typo, that is this would have been written there. So this probability will become xn plus 1 given xn comma xn minus 1. So there are two previous states which governs the probability of xn plus 1. Okay, so we can use these kind of models for text because it becomes more accurate. So depending upon two previous words, you are saying that that will govern what will be the next word. So this kind of text prediction becomes more accurate. Okay, so the more number of previous states dependency you take, the more accurate your model will become, but it will become more complex. Okay, so what is a Markov chain? Over here we are only studying upon the this one, first order Markov chain. Okay, so it is a sequence of random variables where each variable depends only upon the previous state. So if this is the current state, it only depends upon the previous state. So it will be xn minus 1. Okay, so this is it. Examples we have seen. So each state transition to the next state based on the current state, set probability. We can model this as a directed chain of events where each node represents a state of represents a state. So what happens is, you see, we have studied Bayesian networks, so it is similar to that, but each state will have only one edge coming out and one edge coming in. So it will be like this, x n plus 1 and so on and so forth. So this will be a chain. That is why this is known as Markov chain. Any questions? Okay, so I assume it is all right. So you see, these random variables can take multiple values, right? So we can take an example that suppose this xn can take three values: sunny, cloudy, or rainy, right? So xn can take three values. Okay, so this will be curly bracket. Okay, so xn can take three values. Now over here we had represented this as a Bayesian network, that we are saying that from a current state at time point t is equals to 0, we will have at time point t is equals to 1 another random variable. So this is one random variable, this is another random variable. But over here we are talking about one random variable. This random variable can take either value. So we can say 0, 1 or 2. It can either take 0, 1 or 2. Now what is the probability? So it is xn. Now we are saying that x1 n minus 1, the probability of this is actually dependent upon what xn is. So we can represent this as a probability matrix. So what are we saying is the rows of the matrix is what is the value of xn, and the column of this matrix, so the columns of this matrix will be what is the value of xn plus 1. So you see, if xn can take 0, 1 and 2, we say that xn plus 1 will also take 0, 1 or 2. That is, these random variables are identical. That is, the distribution of, not distribution, I'll not say distribution, the range of a random variable x0 is same as the range of the random variable x1, because it is only changing in terms of time. The values it can take are the same over here in this case. Okay, now what I will say is x, so I'll just write xn for better clarity. So xn can take 0, 1 or 2. I can create a matrix. So over here I'll say xn plus 1. So over here I'll write it can take 0, 1 or 2. Okay, so this probability will tell me if xn has taken value 0, what is the probability that xn plus 1 is 0. So what is this probability? This is probability xn plus 1 is equals to 0 given xn is equals to 0. So this is that probability, right? So what will be this probability? This probability will be probability xn plus 1 is equals to 1 given xn is equals to 0. Similarly, what is this probability? So this probability is probability xn plus 1 is equals to 1 given xn is equals to 1. Is that all right? So this kind of probability matrix is known as transition probability matrix. Okay. And this model is actually a transition model. It describes the probability of moving from one state to another state in a Markov chain. Is that all right? If you are facing any trouble or you are not able to understand, please unmute yourself and speak. Okay. So over here I'm saying in a weather model, the probability of a sunny day following a sunny day is 0.8. So can you unmute yourself and speak what value? So where should I put 0.8 in this table? Where will 0.8 go? So 0 is sunny, 1 is cloudy, and 2 is rainy. So where will this 0.8 go? In 6 places over here.
First row, first column.
Over here?
Yeah, correct.
So over here it will be 0.8. Why? Because you see xn was a sunny day, which is 0, and it is asking the probability that xn plus 1 will be a sunny day. So over here this will be the probability it is given. Similarly, probability of it being a rainy day following a rainy day. So what is a rainy day? 2 is the rainy day, and this probability is over here. So it is should be like this. So it should be 0.7 because xn was a rainy day, and we want to obtain the probability that xn plus 1 is also a rainy day. So this is 2. So over here this will be 0.7. Okay. So these are some probabilities I have written. Now one thing you should note that this is a condition. Xn is a condition, right? So xn is a condition. Since this is a condition, this sum, so probability of this plus probability of this plus probability of this should be 1. Okay. So for each row, the elements if you add, that should come up to 1, because xn can either take value 0 or it can take value 1 or it can take value 2. Therefore, the sum of this and this must be 1, the sum of this and this must be 1, and the sum of this and this must be 1. Is that all right? Because this is the condition, xn is the condition, but this is the random variable. It can take either 0, 1 or 2. So given a condition, the sum of xn plus 1 must be the probability that xn plus 1 takes different values, that sum should be 1. Is that all right? Okay. So this is how we write the, so I am writing n and in the this PPT I have written as t, so both are same thing. Okay, you can write it as t or you can write it as n. What is the purpose? The transition model allows us to calculate the likelihood of sequence over time. So we will see this. We will see when we go to the Jupyter notebook, we'll see how are we obtaining, but we'll see the mathematics over here. Okay. So weather prediction model. Okay, I have some, so I'll just, what I'll do is I'll take some blank slides and I'll draw a table. So suppose this is sunny day. So you see over here also I'm drawing a network, but this network is different from what I had earlier. So I'll tell you what is the difference. First, let me draw the network. So this is a sunny day, this is a cloudy, and this is rainy. So I'll just write S, C, and R. This is S, this is C, and this is R. Okay. And what I'm doing is I am saying from sunny to cloudy it is 0.3. From cloudy to sunny it is 0.6. From sunny to rainy it is 0.7. From rainy to cloudy it is 0.5. From cloudy to rainy it is 0.2. From cloudy back to cloudy it is 0.2, and from rainy back to rainy it is 0.5. So this may not be accurate. I have taken this example from an example given by Mr. I don't remember his name. His name is actually Sujan Datta. So he has given some example in his resources. So I have taken this values from his example. So you see this is not a Bayesian network. Okay, this is not a Bayesian network. This is actually a state transition diagram. So what it says is any xn which can take values sunny, cloudy, and rainy can have can transition between different states with this probability. So this is actually a different representation of the same transition matrix. Okay, so let us see how it is. So we are saying this is xn. It can be sunny, cloudy, or rainy. It can be sunny, cloudy, or rainy, right? So what I'm saying is from sunny to sunny it is 0. You see there is no loop from sunny to sunny, so sunny cannot go back to sunny. It may not be true, but since I have this example, so we are going with this example. So if you are at xn plus 1 in a sunny day, you will not be able to move to a sunny day. So xn plus 1 being a sunny day has a probability of 0. So from a sunny day to a cloudy day, the probability is 0.3. And from a sunny day to a rainy day, the probability is 0.7. So this is the 0.7. So whatever the arrows going out from the sunny day, that is what I have written in this row. Similarly, if you are at a cloudy day, the probability that the next day will be cloudy is 0.2. So you can write it over here. The probability that it can be sunny is 0.6, and the probability that it can be rainy is 0.2. Okay. And for a rainy day, the probability that it can be rainy is 0.5. The probability that it can be cloudy is 0.5, and the probability that it can be sunny is 0. Okay. So this is the probability transition probability matrix. Is that all right? Any doubt? Okay, right. So in his example, he has written it in a different way. What he has done is he is saying that, so why I'm following his example, because he has done some calculations and I want to show you that calculations. Okay, so what he has done is he has taken just a minute, just give me a minute. So he has placed uh, 0.2, right? So he has placed cloudy first, and then he has placed sunny, and then he has placed rainy, right? So in this way, he has written the transition matrix. So you can write it in any way. Okay. So this is cloudy, this is sunny, and this is rainy. And if you want to help me write the transition matrix, then it will be a small exercise for you. So what will be the rows of first row? Could you help me? What will be the first row? Cloudy to cloudy, how much it will be? What is the probability that from a cloudy day, the next day will be cloudy?
0.2,
0.2,
0.6,
0.6,
0.2,
0.2. The next row?
0.3,
0.3,
0,
0.
0.7,
Okay.
and then 0.5,
0 and 0.5. Is that all right? Okay. So you see, if you sum the rows, it will become 1. Okay. If you sum the rows, it will become 1. If you sum the rows, it will become 1. All right. Now, what is a random walk? We will see what is a random walk. Now, again, I'm saying this is not a Bayesian network. This is a Bayesian network. This is a Bayesian network. Okay. But this is not a Bayesian network. This is a state transition diagram. What is this? This is a state transition diagram. What is a random walk? Random walk is a sequence of states given a starting state. So actually random walk is a Bayesian network. So suppose we started with a sunny day. Suppose we started with a sunny day. Then you went to a cloudy day. Then you went to sunny back again. Then you went to rainy day. And suppose this is for some number of days you did. So this is actually a random walk. Okay. So this a sequence of random variables which has already occurred or which you can have is known as a random walk. This should be a feasible walk. All right. So you cannot have a sunny to sunny because there is no way you can go to a sunny day if the previous day was sunny. So this should be a appropriate walk. That is what is known as a random walk. Is that all right? Is that all right?
Shubham,
Yes.
Shubham, on what basis you defined the sequence of a random walk?
So it is taken randomly. So you can do it in a computer. Suppose you said that x naught is equals to 0, right? Now you randomly generate a random variable and see what is the probability. So you can take with this distribution. So it is a sunny day. Since it is a sunny day, with this distribution, what you can do is you can take a random variable and you will never come to a sunny day because that the probability is 0. So with 30% probability that random variable will be a cloudy day, and with 70% probability that random variable with a rainy day. So I have taken, so for my example, that random variable came to be a cloudy day. So when it was a cloudy day, 60% probability that next day could be a cloudy day, 20% probability, sorry, 60% probability it could have been a sunny day, 20% probability it could have been a cloudy day, and 20% probability it could have been a rainy day. So for my example, so for this random walk, the random variable took a value of sunny day. So this is how this random walk is generated.
So for example, uh, when the present state is a cloudy, so I can go with means cloudy to cloudy because there is a non-zero probability second
Yes,
row second column. So
yes, yes,
I should have a random walk like this: sunny, cloudy, cloudy.
yes. That can be one example of a random walk for your
Okay,
case.
this can be one of the random walks, correct?
Yes, yes.
So
We are
there is
we are
there
sampling.
is
So this is one sample.
okay.
Now, one question somebody can ask you. So given this random walk, so what is the probability that you observe this random walk? So what will be the probability? You see probability. So this is x naught. So you have to say x naught is equals to s. So over here I have s. I have taken as 0. So I'll just say 0. So this is the probability of the first random variable taking value 0 multiplied by the probability of x1 be cloudy. So what I have written cloudy as 1. So this is 0, this is 1, and this is 2. So x1 is equals to 1 given x0 is equals to 0 times probability x2 is equals to 0 given x1 is equals to 1, and so on. So what is this probability? This is the joint probability. What is this? This is x0 is equals to 0 comma x1 is equals to 1 comma x2 is equals to 0 comma x3 is equals to 2 comma dot dot dot. So you see when x0 is 0, the zeroth state was a sunny day. So I have written x0 is equals to 0. When x1 was 1, then the first state was a cloudy day. When x0 is equals to 2, x0 is equals to 0, the third was a sunny day. So this probability we are interested in. What is the probability? This joint probability. x0 is taking a value, x1 is taking a value, x3 is taking a value, and so on and so forth. So we are trying to obtain the probability of this sequence, and that will be obtained by this multiplication. In the previous case, when we were talking about Bayesian networks, we talked about this, that if you want to obtain a joint probability, it is just the multiplication of each of the probabilities, the conditional probability at that node. So if I go back the previous lecture when we were talking about this, I don't know where I have written it. So is this? Yes. So over here I said that probability SFPPTC. So this is a joint probability. The first random variable is S, the second random variable is FP. So it was what it was. It first was the student has studied or not. The second was whether he has feel prepared or not. The third was did he pass the test or not, and the fourth was did he celebrate or not. What is this? This is actually the product of all the probabilities. So you see, I'll take another color. This probability actually became equal to the product of individual probabilities. This probability times this probability times this probability times this probability. So that is what we are doing over here. The probability of this is equals to the probability of the first. So what is the probability? X0 takes this value, probability x1 takes this value, given x0 is this, probability x2 takes this value, given x1 is this, and so on and so forth. Is that all right? Is that all right? So I'll just write it again because it will be better for you. So what I'm interested in, please ask me questions. All right, huh?
This means actually it is showing that what is the probability of happening of this sequence.
Yes, yes, yes. So someone can ask you, like for example, I have seen this kind of walk. What is the probability that this had occurred? Maybe I was wrong. So what is the probability that this occurred? Some kind of question like that. So you can take an example. This is not an example of, the example I'm going to give you is not an example of Markov chain. It is an example of hidden Markov chain. Nevertheless, so for example, you see an example can be a sensors assume that for 10 consecutive days he saw such kind of data he has observed. So first day he observed some kind of data which indicated him it to be a sunny day. The second day he observed some data which indicated him to be a cloudy day, and so on and so forth. So he can ask a question, what is the probability that this is the sequence which I feel it's correct. So such kind of questions can be asked, right? So we'll see that example as well. I have planned that for today. Okay, so what I'm asking is, given a walk, suppose this is the walk, I'm asking what is the probability of this walk. So it is x0, x1, x2, and x3. What is this? This is actually the product of individual probabilities. Probability of x0, since x0 is not dependent upon any previous state, we are just writing probability of x0 times probability of x1 given x0 times probability of x2 given x1 times probability of x3 given x2. You see, these probabilities are known to us. This transition matrix or this diagram has these kind of probabilities. It has
here px0. In the previous case, we have always decided the state of a value with respect to previous state. But in case of px0, what will be that value?
we
If
will
we
see
go
that.
back to the
No, we will see that today. It is not easy to obtain the value of px0. These values are
Okay,
easy to
okay.
these
Yes,
values
yes.
because we have these values from the transition matrix. We know these values, but we have to obtain these values to get this joint probability distribution, and we'll see how to obtain such kind of probabilities. Okay, is that all right? Now, how can
Okay,
you
okay.
obtain? Hmm. The next question is, how can we obtain such kind of probabilities? Probability of x naught, right? So this is the question. So if you go back, you may remember marginalization, or you can say conditioning, or you can say law of total probability, right? We had seen in previous class probability of an event. Probability of A can be written as probability of A given B times probability of B plus probability of A given B complement times probability of B complement, or you can say summation probability A given Bi sum over I, where union of Bi, so it is actually union, huh? So it is union of Bi is a, so or you can write where Bi, where the, oh my god, where the set B is, or event, where the events Bi are disjoint and collectively exhaustive. I'll tell you what it is. So if you remember this diagram, we saw that if this is the universal set, okay, I'm writing universal set as this, and I'm saying this is A, and what I can do is I can distribute this universal set into multiple B's, right? So I can say this is B1, this is B2, this is B3, this is B4, and so on and so forth, right? So the condition is this union of these BIs should be the universal set, and there should be no overlap between the multiple BIs. So B1 should have no intersection between B2 or B3 or B4. So these two conditions together, all the BIs should be disjoint, and the union of these BIs should be the universal set or the sample space, right? Omega, or the sample space. If these two conditions hold, then you can write it as probability of this times probability of Bi. Okay. So what I'm doing is over here, I'm saying we have two partitions, right? B and B complement. So in this case, I had B and B complement, right? And this was A. But I'm saying it can have multiple different sets, right? We can have B1, B2, B3. Then we can write it like this. So you can obtain the probability of an event A where you are conditioning on another event. So you see, we have over here again these kind of probabilities, but we don't have this kind of probabilities in this Markov chain. You see, we know x1 given x naught, we know x naught given x1, and so on and so forth. This kind of probabilities we have, but we don't have this kind of probabilities. Again, this is one trouble. Are you with me, or is this getting confusing? Right, so what was this? This is actually law of total probability. Yes, you can ask questions. Okay. So we will see another way, or different ways to obtain this kind of probabilities. So where are we right now? So we can have a sample, we can have multiple states together. We know that this has occurred, and what are we trying to do? We are trying to obtain the probability of this sequence, right? We saw that obtaining a joint probability can be done if we have this kind of probabilities. Now what is our aim? Our aim is to obtain this kind of probabilities. Okay, now if you remember, we talked about frequentist measure. What was it? It says that if you don't know the probability of an event A, what you do is you do the experiment capital N number of times, and suppose in this capital N number of times you observed A to be in NA number of times. So in capital N number of experiments, you observed A in NA, then probability of A is approximately given by NA by capital N when this N is more high, which is actually, so you can write it like this. So this is correct. probability of A is equals to limit capital N tends to infinity NA by N, right? So you can use this. What we will do? We will do this experiment multiple number of times. So suppose we generated a random walk with using this transition diagram. Okay. We started with any state and we obtain. So suppose we obtain this sequence S, C, C, R, S, suppose C, R, S, or C, S, and so on and so forth. So you have suppose 10,000, 10 or 1 lakh the states. You did 1 lakh, so that the chain had 1 lakh states. Among those, if you observed, suppose S occurred in 30% of those, C occurred 40% of those, and R occurred 40%, not 40, 30% of those, then you can say the probability of X naught is equals to S is 0.3, probability of X naught is equals to C, which is 0.4, and probability X naught is equals to R is equals to 0.3. So you can tell this. So this is not an accurate way to do it, but we are saying that you can use this idea to obtain this kind of probability. So this is one way. This is the first way of obtaining this kind of probabilities. Okay. This is the first way. Any questions? So we are sampling. Actually, this is what we are doing. We are sampling. Yes, yes.
In this case, to generate the sample state of 1 lakhs data point or states, we need to follow that matrix.
Yes.
Using that matrix, we have to generate this one. Then only we can count and find individual states.
Yes, yes, yes.
Okay.
All right. So this is the first way. And any questions? All right. Now there is a second way to do it. How we can do it? You see, what we will do is you see, what I'm saying here is, what are these kind of probabilities? These kind of probabilities, what we did in the first step, or first way to obtain this. We are saying that we will do n number of samples, but in a way, what are we doing? We are obtaining a chain which has a very long length. The chain length is very long, right? That is how we are obtaining these values, 30%, 40%, and 30%. So we'll use that idea. That is, when the chain length is infinity, then what is the probability of each of the state? So that was the idea in the previous case also, but we'll use that idea and we'll say that transition probability is known as stationary distribution. Stationary probability. So what is this? This probability says X naught is equals to 1, probability this is equals to something, probability X naught is equals to 2, and probability X naught is equals to 0. So this probability matrix, or PMF, probability mass function, this is what is a transition probability. So over here we did the same thing. If you look very closely, we did the same thing. Over here we sampled, but over here what we are saying is we'll use this idea. How will we use this idea? So I'll not explain you the proof of this, but it says that if you use this expression pi a is equals to pi, where pi is the stationary distribution, then if you solve this, then you will be able to obtain that stationary this probability is transition probability, not transition probability, stationary probabilities. I'll give you one idea how it is happening. So you see over here, when I'm saying the probability of S given S, so what I'm saying is probability of x1 is equals to S given x naught is equals to S. I know this to be a value, right? Now what I'm saying is you can go from state S to state S. It was 0, but it can be any value, right? Now this kind of probabilities you can obtain by matrix multiplication. You see, we know pi naught to be, so we will take, I'll just write this matrix over here, that it will be better. Just give me a minute, I'll write it over here. So the transition matrix is 0 0.2, 0 0.6 and 0 0.2, 0 0.3, 0 and 0 0.7, 0 0.5, 0 and 0 0.5. Okay, so this is what? This is cloudy, sunny and rainy. So we are saying this is cloudy, sunny and rainy, cloudy, sunny and rainy. Okay, so this is the transition matrix and we will name it as A. So we are naming this matrix as A and this A is same as this A. Okay, now what I'm saying is fix a state. So this is how we did the sampling. Fix a state. If you fix a state, then what is the probability? Suppose we are fixing sunny. So what is the probability? The probability of the first state is like this: 0, 1 and 0. Is it all right? For the first state we are saying fix it to be sunny and then we'll do the sampling. So if we do this, then this is the probability of the first state. Is that correct? The first state takes S with probability 1 and other to be probability 0. Is that all right? Is that all right?
What is this pi 0? What is it?
So over here I'm writing probabilities as pi. So I'm saying the probability. So this is actually the PMF of x naught, or I can say probability of x naught being cloudy is 0, probability of x naught being sunny is 1, and probability of x naught being rainy is 0. This is the, because we have fixed it, we are saying that let x naught be S. If x naught is S, then what is the, so if x naught is S, then what is the probability of x naught taking different values? That is our assumption. If x naught is S, then this is the probability. If x naught is C, then what will be pi naught? Pi naught will be 1, 0, 0, right? This is the probability of it taking different values. So this is the probability if we are fixing that state. Now I am saying, if this is the case, then you tell me what will be the probability of x1 taking value S. Given this, what is the probability x1 will be S? What will be this probability? You see, you come over here, you are saying x naught is 1, sorry, x naught is sunny. The probability of x1 being sunny is 0, right? We are obtaining like this, 0. Again, probability of x1 is equals to cloudy will be 0 0.3. And probability of x1 being rainy is what? 0 0.7. This is how we can do it. Is that all right?
So pi 1 will be 0 0.3, 0 and 0 0.7.
No. Yes, yes, pi 1 will be, yes. Pi 1 will be, what will be pi 1? 0,
0
0
0.3.
0.3 and 0 0.7. Yes, yes.
No, first will be 0 0.3 because first one is the cloudy.
Yes, yes, yes. First will be 0 0.3, then it will be 0, and then 0
then
0.7.
0 0.7.
I'll show you how we obtained it. Now you see, if you do this, pi naught times matrix multiplication of A, what you will obtain is pi 1. So you can just try. What you do is you write pi naught. Pi naught is what? 0, 1 and 0. And this is the matrix A1. So you do this multiplied by, so this multiplied by this. So this row multiplied by this column, this row multiplied by this column, this row multiplied by this column. If you do it, then you will see, you will obtain this matrix. So you multiply, it will be this multiplied by this. So you will obtain 0 0.3, this multiplied by this, you will obtain 0, and this multiplied by this, you will obtain 0 0.7. So you see, this is what? This is pi 1. Is that all right? Is that all right? Please, you see, it may be confusing. So please ask me questions. Right? So you have
It's
obtained.
fine. It's fine.
Now you can obtain pi 2. How you can obtain pi 2? You just do pi 1 times A. If you do this, you will obtain pi 2, right? If you do pi 1 times A, you can obtain pi 2. You can do pi 2 times A, you can obtain pi 3. Is that all right? Is that all right?
If we do pi 1 times A, and then only it will be all right.
Then we can obtain pi 3. That is what I mean.
No, my point is, if we do once, then our realization also will be better. Pi 1 into A.
Okay.
And then if we relate our understanding.
Okay. So we can just multiply So what is pi 1? 0 0.3, 0 and 0 0.7. And this is the matrix. So you can just multiply the row with this column, the row with this column. You will obtain some numbers. Whatever you obtain, suppose it was A1, A2, A3, whatever this is, it will become pi 2. That is what I mean. If you multiply this by A, when you obtain this, suppose it became A1, A2, A3, that is what pi 2 is.
Okay.
Okay, so now the idea, so this is not the idea. What is the idea? You see, we want to obtain the long run average. It is known as long run average. So what we want to multiply this, we want to do this multiple number of times such that this that is pi n minus 1 times a becomes same as pi n minus 1. So this and this, or I can just write pi n for the time being. I can just write pi n such that pi n minus 1 becomes same as pi n. So this is the idea. What I'm saying is we will multiply this so many number of times such that the probabilities become same. So we are doing it infinite number of times and then that will become the same. So over here this is known as the stationary probability. When this happens, pi n plus n minus 1 becomes same as pi n, then that probability which we obtain is actually the stationary probabilities. Okay, so this is the idea of obtaining the stationary probabilities. This probability, this probability, this probability. So we are using the same idea, same idea over here.
Shubham,
Yes.
if we are trying to obtain pi n same as that of pi n minus 1, that is stationary probability, then means, in other words, you just mean to say that irrespective of weather condition, if if today is a sunny day, tomorrow shall be a sunny day. Is it
No,
like that?
no. The probability of, so
No,
what?
actually, I think it is something like iterative way. The finally the error will be zero. Means from one
Yes,
state to next state, if we move, that error calculation will be zero. Means we have already reached to the final state.
final state. But his question is little bit different. I think he is
Yes,
asking.
yes.
So see what is this?
Probability of previous state is equal to probability of current state. We are supposed to perform the iterations ideally infinite number of times so that we can obtain probability of current state is equal to probability of previous state.
So
Correct?
this stationary probability means that in the long run, this Markov chain will stabilize with this probability. This will be the probability of each of the states. So if you do n number of times, 70% of the time it will be sunny day, 10% of the time it will be cloudy day, and 20% of the time it will be a rainy day. So that is the stationary distribution. This is a property of a Markov chain, stationary distribution.
Okay.
Every
Okay.
Markov chain has a stationary distribution and it is an
Yeah.
equilibrium state.
It's a probability mass function, not a probability. Means mass function of previous state is equal to mass function of current state.
When this happens, then it becomes a stationary distribution.
Okay. Okay.
Okay. And now over here we are talking about mass function because this random variable is taking discrete values. If it is a continuous random variable, then we would have talking about distribution functions or density function. I'm not going on into all those things. The idea is to make you explain. Okay. So there are two ways we have talked about.
But I have one doubt. I have one doubt.
Yes.
Can you provide? Pi 1 into A, pi 1 is 0.3, 0.7. Whenever this will be multiplied with the A, say for the first column,
Yes.
means we are multiplying with the rainy and rainy, but we are trying to find out the probability of cloudy. Means if we do the
So
means
let us multiply. You will get a number.
yeah,
It will,
better to multiply once.
okay. So the first multiplication we did were pi naught times a, then we obtain this pi 1, right?
That is easy to understand because we are starting from one state and that state is multiplying with the other factors where that state is there, corresponding to that state is there. So the finally we are reaching to that row only.
So I'll just do the multiplication quickly. Just let me do.
Pi 1 into A.
I'll just do the multiplication quickly. So it will be 0.3 times 0.2 plus 0.7 times 0.7 times 0.5, right? 0.5. So it is 0.41. I'll just remove this A1 to be 0.41. What is A2 then? A2 will become 0.3 times 0.6. Just a minute. 0.3 0.6, and yeah, it will be 0.18, right? And then it will become, the next will be 0.3 times 0.2, 0.3 times 0.2 plus 0.7 times 0.5, it will be 0.41. All right, so this is the probability of pi 2. Now what is the doubt?
Doubt is this one, that here we are multiplying with the rainy probability of 0.7 with the cloud, means under rainy. Okay, under rainy, the next one is the cloud. So yes, okay, fine. Means
Right?
if the condition is rainy, that rainy probability is 0.5, then we are trying to find out the probability of cloud, then we are adding to find out the probability of cloud.
Yes. So it is similar to this, what we are doing over here.
Yes. Fine. Okay.
Right? So over here, you see these numbers will actually converge to some values. When it converges, then it becomes a stationary distribution. We will do this and it will converge to some values. It might occur that some Markov chain doesn't converge to that value. In that case, it doesn't have a stationary distribution. Some Markov chain may not have stationary distribution. All right.
By chance, if it is positive, negative are there, then oscillation kind of things may happen.
Negative cannot, because this is oscillation can occur, but negative probability will not be there.
Negative may not happen.
Right. Now, one more point of caution. If you solve this equation pi 8 equals to pi, if you solve this equation, you can get multiple roots. Okay, so this is very similar to linear algebra if you have seen eigenvalue and eigenvectors. So this if you solve, you can get multiple values. You will only take that value of pi where the sum of these three is 1. All the other, so if you have three such values, because you have a 3 cross 3 matrix, you will obtain three values of pi. Okay, there will be three eigenvectors. So you will have three different vectors for pi. Okay, it will be one vector, two vector, and three vector. So only that vector you should take where the sum of these individual probabilities becomes 1. The others will not become 1. Okay, if the others are also becoming 1, then it is not a stationary distribution. Okay, so when this sum becomes 1, then only it becomes a stationary distribution. All right, so this is the second way of obtaining stationary distribution. Is that all right? Any doubt? And the third way we have already seen, so I'll just write it over here. The third way we have already seen, you can multiply this. So you can do this matrix multiplication, suppose 10,000 number of times, and whatever you obtain pi 10,000, you can take this as the stationary distribution. So in computational work, you can either solve this equation. So over here, actually, you can solve this equation. Either you do this some number of times, or you do sampling some number of times. So you have three ways to obtain the stationary distribution. Okay. You have three ways to do the stationary distribution. Any doubt? All right. So what we'll do is, before I proceed, I'll show you one code I have written where I have a transition matrix, and we are trying to obtain, first we are trying to obtain the stationary distribution, and then what we are doing is we are trying to obtain the probability of a sequence. So then it will be clear. Otherwise, mathematics, it may become a lot. Okay. So we'll see that now. So I'll just show you. And if you have doubt with the code, you can just ask me. I'll try to explain whatever I can. Is my screen visible? I guess it is visible, right? My screen is visible, right? Yes. Okay.
Yes, yes.
So you see, I have already written some code. I'll just go through over here. So what I'm saying is, so over here I've taken a different distribution because that distribution was not totally correct. I was saying that from sunny to sunny, the probability is 0. So that may not be correct. So I've taken some random distribution. Doesn't matter. For practical application, it may matter, but for understanding, it is all right. So I'm saying that sunny is state 0, cloudy is state 1, and rainy is state 2. Okay, so this is the 3 states, and we need some installation. So if you are trying to do this, you have to install this scipy library. Okay, so this is the transition matrix. I have written the transition matrix. So the first row, first column, this is actually what, x naught being or xn being 0, and what is the probability of x1 being 0. So that is this. Okay, so there is a 70% chance of staying sunny given the previous state was sunny. There is a 20% chance being cloudy given the previous state was sunny, and there is a 10% chance of being rainy given the previous state is sunny. Okay, so what I'm doing is I'm calling this numpy library. So this library helps in matrix manipulation and everything. So this is a very popular library in Python, and this is actually a dictionary. So I'm saying states. When I say 0, I mean sunny. When I say 1, I mean cloudy. And when I say 2, I mean rainy. Okay, so this is what the states I'm defining as a dictionary. Okay, so I'll just start afresh. So I'll say kernel restart. I'll start again. So this is the starting. So you see I have run this. Now if you see, I'll just help you to explain this. So if you say stat state, when I say 0, then it will give me sunny. So you can just index into a dictionary. Okay, so we are indexing. So this is key. So in a dictionary, this is known as key and this is known as value. Okay, so what is a dictionary? Dictionary is a key value pair. So when I say 0, it means sunny. When I say 1, it means cloudy, and when I say 2, it means rainy. Okay, now this is the transition matrix. So I'm storing it in a variable name a, which is, so this is the 2-dimensional list. It is a list of list. Over here, one column. So the way I have written here, the same way I have mentioned over here. All right, but it is a list of list, and this list I'm converting into a numpy array. So this numpy array is kind of a matrix. Okay, in Python. So Python uses numpy array for efficient matrix manipulation. By the way, I'm not able to see your if you are raising hands or not. So please speak up if you have any doubt. Now I will do a random walk. So what I will say is I will do a random walk of length 15. So I'm saying the start state is 0. So let the first day be a sunny day. And okay, what I'll do is I'll clear all output such that I'll generate the output in front of you. I have cleared the output. So okay, now we are here. We are saying that we will generate a random walk of length 15. The start state is 0. What I'm doing is I'm saying the current state is equals to start state. So I'm defining a new variable called current state, and I'm saying, so I'm printing this. What I'm printing is state, current state. So current state is actually what? 0. And I'm printing an arrow. So I'll just break this to show you what it is doing. Split cell. So what it is doing, it is printing like this, sunny arrow. Okay, but I don't want it to be split. So I'll just write it over here. Now what I'm doing is while loops. I'm running a while loop until this becomes 0. So what I'm doing is I'm saying the current state will be taken from this 0, 1 or 2. So it is a randomly taking any value between 0, 1 or 2 with probability a current. So what is this? We are indexing into the matrix. So when I'm saying a current, Python is taking as a, what is current right now? Current is actually 0. So it is doing a0. And what is a0? A0 is this row. So with this probability, this np.random choice will take any value 0, 1 or 2. Okay, what is the distribution? This is the distribution. With this distribution, this random choice will sample from this values 0, 1 or 2. With probability 0.7, it will take value 0. With probability 0.2, it will take value 1. With probability 0.1, it will take value 2. And then we will print. okay, and we will decrease the value of n. Okay, so this is how the random walk is occurring. So it was sunny, 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 rainy, sunny, and so on and so forth. If you run this multiple number of times, you can have different um, random walk. You can change the start state as well. Suppose you started with 1, so you will have a different random walk. If you start with 2, then you will have a different random walk. Okay, any doubt over here? All right, so first is known as the sampling. So first we will do sampling. Okay, so this is, here I am doing sampling. So we have talked about 3 ways to obtain this stationary distribution. Over here we are trying to obtain this stationary distribution pi. Okay, now what I am doing is I will sample 1 million states. So 10 to the power 6, this is how we write in Python, 10 to the power 6, and we'll start with state 0. Now what I'm doing is I'm saying let this be the current state. Initially the state count, so we are counting in this sample what is the count of the sunny state, what is the count of the rainy day, what is the count of the, sorry, what is the count of the cloudy day, and what is the count of the rainy day. So the first index is of sunny, the second index is of cloudy, the third index is of rainy. And since we are starting with state 0, then we are saying that this count for the first this start state, make it 1, because we are starting with that state. And now again we are just sampling, and then we are counting the number of each time we encounter a state we count it, and since we are counting, we have to divide it by the total number of steps we take. So we are dividing it, so it is just like that. So we are doing this, whatever this step is, so this step is 1 million, so we have done 1 million experiments. Out of those 1 million experiments, some number of time we'll encounter this, some number of time we'll encounter this, some number of time we'll encounter this, and to obtain the probabilities we will divide each of those by 1 million. Okay, so this is what we are doing over here. It will take a little bit time because it is doing 1 million iterations. Any doubt over here? So this is the approximate long range probabilities. It is 0 0.5, 0 0.3 and 0.18. Any doubt? Okay, so I assume it is clear. And by the way, whatever I'm showing you is an example by Sujan Datta. So I have taken all examples from his example. Okay. So this is the repeated matrix multiplication. I told you a different way of obtaining the same thing. You take one state, you say that this is the probability of the starting state, and then you do repeated multiplication, matrix multiplication. So how many times I'm doing matrix multiplication? I'm doing 1000 number of times. And initially I am saying this is the initial or the initial transition matrix. And what I'm doing is I am multiplying the matrix with itself. This np.mtmul is actually a matrix multiplication. So I'm multiplying the matrix by itself. And when I multiply the matrix by itself, the rows of the matrix will be the state transition. So I'll just show you without printing. So you see it converges. So each row converges. This is actually same as this, and this is also actually same as this, which is the transition probabilities. What it means, this transition probability does not depend upon the start state, whether you start with sunny or you start with cloudy or you start with rainy. Whatever you start with, it doesn't matter. The long run average will be same, because it is a property of the Markov chain. This transition, not transition, this stationary probabilities is a property of the Markov chain. That is, in the long run, this number of times will be sunny, this number of times will be cloudy, this number of times will be rainy. It doesn't depend upon the start state. So you see, when I have done the matrix multiplication, whether you start with sunny or you start with cloudy or you start with rainy, the stationary probabilities becomes the same. That is why I am saying you take any row, it doesn't matter. And this is what the probability obtained with this method is. You see, they are very close to each other. Both of them are very close to each other, right? Any doubt? Any doubt? Okay. Now over here we will do the eigenvector multiplication. So over there I showed you one more method, pi a equals to pi. So this is a package where I am calling this linear algebra. So from SciPy package or library, you can say, I am calling this function linalg. This is actually a linear algebra, and the function is actually EIG. What it does, it obtains the eigenvalues. So if you are not able to understand what eigenvalues are, doesn't matter. It will just do the multiplication. What it will do is it will do pi times a. It will do this pi times a. This is what it will do. And why I am saying right is equals to false, because you can have two kind of multiplication. Either you can have a times pi or pi times a. So over here when I say right is equals to false, then this side will not be multiplied. Left is equals to true, this side will be multiplied. So in the matrix we are doing left side eigen multiplication. Okay, so this is what we are doing and this is not what we are doing. So, and we are storing the values over here. Okay, so I'll just show you. So this is the eigenvectors and these are the eigenvalues. Okay, so you see we have three vectors. So I told you when you solve this equation, you will obtain three values of pi. The first value is this row, this column, the second is this column, and the third is this column. Okay, you have to take that value of pi which has this. So this columns of the eigenvector must also satisfy the probability distribution. So if you sum of those probabilities, you must be equal to 1. Now you can see that none of these sum equals to 1 because we have not normalized it. In this case this is negative, so this cannot be a probability. In this case this is negative, so this cannot be a probability. So only the second column is actually the column which we are interested in. So what we'll do is we'll normalize. How are we normalizing? We will say we will sum these three up and we'll divide it by the sum. Then we are normalizing it to 1. So currently suppose the sum is whatever it is. So it is what 1.6 is the sum actually. 8 plus 5 plus 3, it is 1.6. So we'll divide it by 1.6 and then we'll be able to obtain the probability. So you see these are pretty close, 0.5, 0.3125 and 0.1875. And you see this is not the accurate one. So sampling is not actually giving you accurate one. Matrix multiplication is giving you somewhat accurate, and eigenvector will always give you. And these are errors, by the way, 0.00001. These are Python errors. Okay, these are not mathematical errors, these are Python errors. So this is how you obtain sorry so this is how you obtain what I was saying, stationary probabilities or stationary distribution. Is that all right? Okay, I assume it is all right. Now what we'll do is we will see, suppose this is the chain we are interested in, or the long run we are interested in, cloudy, rainy, sunny, cloudy, and we are asking the question, what is the probability that this sequence has occurred, this sequence has occurred. So what will be this, what will this be? We will multiply x naught is equals to cloudy times probability x1 is equals to rainy given x naught is cloudy, and so on and so forth. We'll do this, and I have just done the same over here. I am just multiplying. You can read this function. We are just doing the same thing. We are obtaining, so we have obtained this distribution pi normalized. We will pass this pi normalized to this. Why are we passing this? Because the initial state we have to know the probability. That is why we are passing it. And for the other probabilities we can use the transition matrix. So we are also passing the transition matrix. So to this function we are passing the stationary distribution, we are passing the transition matrix, and we are passing the sequence. This is the sequence 1 2 0 1. So cloudy was 1, rainy was 2, sunny was 0, and cloudy was 1. So we are passing the sequence, we are passing the transition matrix, and we are passing the stationary distribution. And if you just go and read this, it is not very difficult. We are just doing this multiplication, this times this times this times this. Okay, if you do that, then you will see that the probability for this random walk is 0.0375. Is it all right? Is that all right? Please let me know if that is all right. Okay, if that is all right, then we will see one more example, which is very good example of using a Markov model. Again, these examples are all inspired by Mr. Sujan Datta. So over here I have given the necessary packages you need to install before running this code. And I have used the resource from Kaggle. What is Kaggle? Kaggle is a online platform where you can where you have multiple data sets and other competitions and everything occur. You can just go there and see what Kaggle is. This is very popular, by the way, in machine learning community. There is a lot of data sets and most of them use these data sets. And we will use one more module which is known as NLTK, Natural Language Toolkit. And in this we will do natural language processing using Markov chain. You see, Markov chain is actually a stochastic model, right? It doesn't have any information, complex information about language. It will just do the whatever we are doing over here, we are doing it using Markov chain, just using the statistical analysis, right? Just using the stochastic model. But still you will see it performs so well. Okay, we will see that. So what I'll do is I'll clear everything, restart and clear everything. So these are the, so I'll start from here. So these are the imports we are doing. So one is NumPy, which will be used to do matrix multiplication manipulation. This pandas is also a very popular library in Python, which is used for data frames. It is similar. So data frame is very similar to what we have our data in Excel. So lot of similarities are there. OS is used to access my files in the computer. RE is actually used to do some refining in the text. This string is actually strings in Python, you know, right? When we write anything in inverted commas, it becomes string. This NLTK tokenizer, we are using it. We will see where we are using it. And this random is actually help us generate random numbers in Python. Okay, so over here in this block of code, so I'll just run everything. So in this block of code, what are we doing? We are going to this path. So this is a path in my computer, user Shubham Keshri dot everything what is there. This is a path in my computer. And in this path, there are some files. So for this Alice in Wonderland, there is only one file. I'll show you the file. This is the file. It is a text file. Okay. So this is actually a novel. And the novel is actually Alice in Wonderland. And this is the text file, which I have in that location. Okay. So that file it is accessing, and what it is doing it is taking each line of that file. So what it is doing, it is taking this line and then it is taking the next line. So line by line it is extracting from this text file. So you see, we are opening that file, and for this file we are doing for each line. So we are extracting line from that file, line by line, and then we are stripping. So stripping is a function which removes spaces from the ends of the line. So suppose there is some space over here, right? There is some space. So strip will remove the space from the starting and the end of the line. So we are just doing some cleaning. So we are just doing some cleaning, and we are just, this is also cleaning. And what are we doing is, we have a list called txt. So in this list, we are appending the line. So each element of this text will be a line from this novel. Okay, I'll just show you. So it has 26 number of lines, and I'll just show txt, and I'll not print everything. Suppose I print the first 9 lines. Sorry. Okay, we have named it as stories. So you see, Alice in Wonderland. So it is actually taking the lines. Alice was beginning to get, this is this line. Alice was beginning to get tired by her sister and all, right? So it is taking line by line and it is storing it into this stories. So it has 2726 lines or objects in this, not objects, elements in this list. Is that all right? Is it all right? I'm trying to go a bit slow. Is it all right?
Yes.
Okay. So yeah, this is it. Then what are we doing is we are cleaning the text. There may be some punctuations and everything. We're just, so over here, what are we doing is we're taking each line from the stories, this variable, and we are putting it into lowercase. I am putting it everything into lowercase. Then we are doing some cleaning. So we are removing. So this RE is reused over here. It is removing these kind of special characters. And here, when I saying word tokenizer, this is actually used from NLTK. What this word tokenizer does is, I'll show you. I have an example. So this is the word tokenizer, and I'm calling the word tokenizer, and I'm passing a text to it. And what I'm doing is I am passing this text or this string to this word tokenizer. And you see what it does. It separates each of the elements from this text. Okay, so this word tokenizer is actually separating each of these elements individually. So this is what word tokenizer does. So for each of the line, for each of the line, so I have done this cleaning. For each of the line, I am extracting each of the words. Okay, so for the whole novel, I have extracted each of the word and then stored it into cleared stories. Okay, so this is the variable where I have individual words from the novel. So this has how many words? It has 26434, 26,434 words. We had 2,726 lines, and after removing the special characters and tokenizing, we have 26434 words. Now we will make the Markov model. Until now we have not done anything related to Markov model. Over here we will do the Markov model. What are we doing is, over here I am saying not one word, I'm saying for two words make a state. So for example, this is the these are the four words I have in cleared stories. So take two words and make it one state. Again, two word, make it one state. Okay, so that is why I'm saying n grams is equals to 2. So for each two word, why I have taken two words? Because the context will be there. If I only take one word, then the context will be removed. So I want to have some context of the language. That is why I have taken two words. You can take three words, four words, and so on and so forth. So for two words, we are making it one state. And then what are we doing is, we are creating transitions. So for example, if I write a text over here, so suppose this is the text I have, and I'm separating it into two words. So this is the first word, this is the second word, sorry, this is the second state, this is the third state, and so on and so forth. Sorry. Okay, so I'll just print some words. So this is the words I have, right? Now this is single words. So what I'm doing, I'm take two words. So take two words each and draw the Markov model. How are we doing the Markov model? So suppose I am here. So I saw Alice was. Now these two words is a predecessor of these two words, beginning to. Similarly, somewhere else maybe, so I'll just copy this, Alice was, and I'll see where is the next Alice was. Alice was over here, and the next two words is not a. Similarly, the next Alice was is not going. So we have Alice was, and it moves to multiple states. The first state was, what was the first state? Beginning to. The second state was not a. The third state is not going. The fourth state is soon left. So from Alice was, we have multiple arrows going. So we are, what are we doing? We are drawing the transition diagram. So Alice was one node, and all the nodes it is preceding, we are drawing the arrows. So suppose there are, so how many arrows are there? Let me see. There are 16. So see, Alice was follows 16 different states over here. If you see 16, is it visible? The 16 is visible, right? So we will have from Alice was 16 different arrows to 16 nodes. And then what we can do is, we can obtain the transition probability for these arrows. So that is what this model is doing. For each of the pairs, it is creating how many next node it is going, and then it is creating the probability. Okay, so this is how we are obtaining the Markov model. And then this Markov model has 14,548 states. And now if I say the rabbit, what is the successor of this, this the rabbit, how many edges are going from the rabbit? So you can see from the rabbit, one arrow goes to say to, the other arrow goes to actually took, the other arrow goes to was no, and what is the probability? These are the probabilities. So with this probability, the rabbit state transitions to say to state. With this probability, the rabbit state moves to actually took state, and so on and so forth. Is it clear? So this is how we have built the Markov model, right? Now we will what this is doing is we are using that Markov model and we are doing a random walk. So we have understood what a random walk is. This function is just doing a random walk, just doing sampling. You see, it is taking a start state, and then from the next state, it is actually doing random choice using this transition probability. So it will take you some time to understand this code, but what it is doing is from the current state, wherever it is going, so from, suppose from the rabbit, it is going to this and so on and so forth, so many states. So it will come over here in this area, and these probabilities will come over this area, and this random choice will take one of those states with this probability distribution, and this is a random walk. So it will do for the number of times you are asking it to do. That is the limit. Okay, so what I'm doing is I am saying, if I pass the starting state as rabbit and I want 8 words. Okay, so I'll just print once, then it will be better. So if I say generate a story with the starting state of the rabbit with 8 states, that is, it will be 16 words actually. So what it is doing is it is taking, this is one state, this is another state, this is another state, and if you count, it will have 8 states or 16 words. And this is the sentence it has generated. The rabbit was no longer to be seen. She found it very hard indeed to make out which. So you see, it is not accurate, but it has a logical structure. And we have not used any high level technique to generate this sentence, right? It is just a Markov model. Now what I'm doing is I'll generate 20 such sentences. So this is 20 such sentences starting with the rabbit. The rabbit asked, no, I did. So some of them will not make sense, or most of them will not make sense. But yeah, it is able to do it. The more data you give it. So over here, what I have is 26,434 words. The more data you give it, the more better it will become, right? Next, what I'm saying is the start state is there where, and generate again 8 states and do so for 20 number of times. So you see, you just read few of those. There were 3 little sisters. You can just see it makes, it will not make sense, but it has a good flow, good structure. Again, starting with the queen. So these are the sentences we have generated. The queen turned crimson with fury, and after a minute trying to touch her poor little, something like that. So you see, there is some structure. Now we'll generate a story. So it says Alice was, start with Alice was, and I've given a limit of 100. So this is the story it has generated. Alice was only too glad to find herself talking familiarity. So you see what you can see, right? How it is performing. So all of these are random walks, by the way. All of these are random walks. So this example I have inspired by this example. So this has a more richer library. Okay, so I'll just clear all output, and this I have taken directly from this source. Thanks for sharing from Sujan Datta. And what it is doing, this library is actually Sherlock Holmes stories, and it has multiple Sherlock Holmes stories. So over here it has only one novel, right? It had only one novel, Alice in Wonderland, but this whatever data I am giving, it has multiple stories of Sherlock Holmes. Okay, so we will do the same thing. It has 4,30,000. No, it has 4,30,042 number of lines, significantly larger than what we gave over here. It had only 2,726 lines. Okay, so we'll clear the data. Just a minute, I'll just restart. I did some error, I guess. Okay, so I'll run each one by one. So you see how many.
I have one.
Yes, yes.
I have one thing that in this case, if we means give the input in different way, means little bit different way, means let the full stop wherever the stop is there. Beyond there, if we stop the word, no need to consider the next word, then the accuracy also may be better. Means there will be a jump from one sentence to another sentence. Will it
So
be?
we have removed the full stop. You see, these are actually.
So if no, you have removed, we have removed, but we can make that algorithm in such a way that wherever full stop is there, then let it consider only single word. After that, again, it can start from the double word. Means
So
there the
that will not be a Markov model. Markov model says that. So over here I am saying first order Markov model, and what I am doing is I am creating two words into one. In that
means
case,
whatever it will come, let it come. Means
yes,
we will not give our knowledge input to this model. That
we can
model,
we can give that, but it will not be a Markov model maybe.
it
So
will
you are
not be a Markov model.
higher level. So we are not using those higher level techniques now. This is a very basic statistical model, or stochastic model rather, right?
Yeah.
What are you doing? You're improving this model, right? So that is what
Yeah.
we will see when we proceed in this course.
Yeah, so it is even if, because of which it is not able to means mention where that line should get stopped. It is continuously generating the next 100 words.
Yes, yes,
Like this.
yes, yes. It is just doing a random walk. Whatever we have
Okay.
seen today, it is doing that. Okay.
Okay.
So
Okay.
we'll start seeing. So you see, it has how many number of words, by the way? 46 lakh 64,496 494 words. Okay. And these are the number of states: 2 lakh 8,717 states. Significantly more than what we have given earlier. Okay. So we see what we are doing. We are saying that we will start from dear homes, and these are the sentences it is generating. Dear homes, am I to do, or something like that. Then my dear fellow, that I am. So similar idea, similar concept, everything same, different data set. All right. So we'll move to hidden Markov models. Is that all right? We'll move to hidden Markov models. Otherwise, we'll not be able to complete today's. By the way, any doubt, we'll not hurry up if there is some doubt. So we can just take a minute and then we can start again the next class. So hidden Markov model is actually an extension of Markov model. All right. What it is doing is hidden Markov model. So I'll just give you an idea, by the way. So I'll just give you an idea. So you see, we know what a Markov model is. Right? We know what a Markov model is. Now what we'll say is this is hidden to us. So the example which I gave you, that there is some weather going on, but we will have a machine which has sensors. It does not know what the weather is, but it has data, sensor information, right? So it has an observable state. It doesn't know what the real state is. These are real states, right? These are hidden from the robot or the machine, whatever you call it, the agent, AI agent. But it has other information which is dependent upon the real state. So if this is the real state, there is some state, suppose we are calling it y0 and this is x0. So y0 is dependent upon x0, and using y0, because y0 is known to us, using y0 we will try to obtain some probability of x0 or some sequence of x's. So this is how a hidden Markov model works. Right, so this is how the hidden Markov models. We have information about this. We know the probability. So suppose the sensor, so y naught can take three values, suppose 0, 1 and 2. So the sensor has information that it saw 90 with 90% probability, and it has some error, suppose 0.5% probability with this and this. So this is the information the sensor has, right? The sensor can have this kind of information. With 90% probability, the sensor thinks that y naught took value 1.
That has to be 0.05, 0.05.
Oh, sorry, yes. Okay, so this kind of informations we have, or we can have sequence of information. So we can have three different informations, y0, y1 and y2. Now we are trying to obtain what is the probability of, so given, so we are, what kind of probabilities we are interested in? So we are interested in probabilities of x's given y. This kind of probabilities we can have. So it can have multiple x's or give one x's or something like that. So we can have probability of x2 is equals to something. So I'll just write x2 comma x1 comma x naught given y2 comma y1 comma y naught. These kind of probabilities we are interested in. Any doubt? Any doubt?
Shubham, hello.
Yes.
It is understood that probability of x given y, but how to interpret probability of x2 comma x1 comma x0?
We will see that. That's what we are interested in when we are studying this kind of models. Okay. So I am skipping the text. You can read the text. If you have doubt in the text, you can ask me in the next class. I'll just go forward and explain. Okay. So suppose, so over here what we did, this is a Bayesian network, by the way. This is a Bayesian network. We will not draw the Bayesian network now. We will draw the transition diagram. Okay. These two are different things. Looks similar, but these two are different things. So suppose this is rainy, this is cloudy, and this is sunny. And what is the sensor information? Suppose the sensor has two information. You can call it anything, positive and negative. Okay, so some kind of sensors are there that can have only two values, positive and negative. For simplicity, you can have multiple values, positive and negative. So what I'm saying is, from rainy to rainy, it can go. From rainy to cloudy, it can go. From cloudy to sunny, it can go. From cloudy to cloudy, it can go. From sunny to rainy, it can go. From rainy to sunny, it can go. From sunny to cloudy, it can go. Everything can happen, right? So this is what I have given. And from, suppose sunny to rainy, it cannot go. From sunny to cloudy, it should go, and from cloudy to rainy, it should go. And what, this is also dependent. So when given, so what is this? Probability of positive given rainy. So this will be here. So it will be here. So this will be like this. Suppose I'll use different color maybe. So can anybody tell me what is this probability? What is this probability? What is this probability? So this is a transition, right? From the this to this. So what is this? This is actually probability of
Probability
negative
of minus given s.
Yes.
And sunny.
Yes. Okay. So this is what I have. Now I'll just erase this part. This is known as the hidden state. And this is known as the observed variable. Okay, so because we observe this, the sensors will observe this and it will try to obtain some information about the hidden state. Okay, so hidden Markov model is what? Hidden Markov model is Markov model where there are hidden state plus observed variable. Markov model plus observed variable with Markov model with hidden state with observed variables. Okay, so this is what a hidden Markov model is. So what I'll do is I will take one more page and I'll draw the, so let the diagram be here. I will just draw the mention the probability transition probabilities. Okay, so I'm mentioning two different, for one for the hidden state, another for the observed, you can say state as well. So this is sunny, let me write it as it is. So what I have here: rainy, cloudy and sunny. This is rainy, cloudy and sunny, and this is positive and this is negative. Okay, so these are the transition probabilities. So I'll take a different color. So this is 0 0.5, 0 0.3, 0 0.2, 0 0.4, 0 0.2, 0 0.4, 0 0.0, 0 0.3 and 0 0.7, and these probabilities are 0 0.9, 0 0.1, 0 0.6, 0 0.4, 0 0.2 and 0 0.8. So what does this mean? What does this mean? It means that when the hidden state is sunny, given that the hidden state is sunny, the probability, so what is this probability of positive given the hidden state is sunny? Is that all right? Is that all right? Okay, I assume it is okay. Now I'll ask you a question. I'll ask you, probability of, so what I'm asking, the question is, I have observed some states. What is the probability that X was, so I'm asking the question, or you can ask a different question, by the way. So you can ask a question X comma Y, you can ask this kind of questions. What is this question? It is a joint probability distribution. You are saying what is the probability of this? So suppose this is the chain and you have observed these values, these values, and you are asking what is the probability of this joint distribution. This kind of probabilities you can ask. So you are saying I have observed this kind of variables. I think that these are the different hidden states it can be. What is the probability that this configuration is there? Okay, so these kind of probabilities you can obtain. Other kind of probabilities which you can obtain is, so you can obtain this kind of probabilities. Probability, what is the probability that Y is this given X is this? So suppose the hidden states was this sunny, sunny and cloudy, and the observed state is negative, negative and positive, right? So you're asking what is the probability that negative, negative, positive given that it was sunny, sunny, cloudy. So you're asking the accuracy of your sensors. You're saying that I observed that it was sunny, sunny, cloudy. What is the probability that my sensor will give me negative, negative, positive? Okay, this kind of probabilities you can obtain. How can you obtain? We will use the same idea. We will say, you see, this is actually a conditional probability. First we will see how we'll obtain this, then we'll see how we'll obtain this, then it will be better. Okay, so I'll just remove this first. Okay, we'll not remove this, we'll say this is as comma, otherwise you will get confused. So what I'm saying is, what is the joint probability of this occurring? So the sensor observed this and the um, uh, real thing this happens. What is the joint probability of this? So how will you obtain joint probability? We have seen over here how to obtain joint probabilities. We'll just multiply everything. So how to obtain joint probabilities? We'll multiply individual probabilities, giving taking care of the conditions. And since we have Markov property, then these conditions we can break. We can only have the previous condition. So what will this be? It will be probability of, so we'll start from the initial state, probability of S. I'll not write like this, I'll write like this. Probability of x naught is equals to S times probability of, so we have written the initial state for this. When we write the probability of this, what it will be? Y naught is equals to negative given x naught is equals to S, right? Because this state depends upon x naught times, for this when you write, you have to write probability x1 is equals to S given x naught is equals to S times probability, for this you have to write y1 is equals to negative given x1 is equals to s times probability. For this you have to write x2 is equals to c given x1 is equals to s times, for this you have to write probability y2 is equals to positive given x2 is equals to c. So we can obtain these probabilities, right? We have these probabilities using the matrix. You see every probability we have using this matrix and this matrix. Only for this matrix you have to use the idea of stationary distribution, and you can obtain this probability as well. Isn't it correct? Right? Now the next question. Now the next question can be given some value of observed variables, probability given some not this given so what given some observed variables, what is the probability of x? These kind of probabilities we are interested in now. The second part which we are asking. We have observed some things. What is the probability that the real world were like this? So now you are not asking the accuracy of the sensors. You are saying that my sensors has seen this kind of values. My sensor is sending me this kind of values. What is the real state of the world? This question you are asking, right? Is it correct?
Yes, in the first case, we can say sensor is working proper or not. In the second case, we are predicting the situation. Means
the sensor has given you some information, that is the condition you have, and you are saying what is the probability of the x being this real state.
Application of the yes, application of the previous one was the measurement of the accuracy of the sensor. Means the outcome was. And here the prediction of a situation given a sensor data.
Yes.
The applications are different in these two cases.
Yes. Okay. So you see, you can write this as probability of x comma y by probability of y, right? You can write it like this. This is actually just probability of a given b, which is equals to probability of a intersection b by probability of b. This is it. This is the conditional probability. So you can write this as this. Is it all right? So probability of y is actually a constant. You know that. You know the accuracy of your sensors. So for the time being, we will ignore it because we know the probability of the accuracy of the sensors. So for the time being, we'll ignore it. We will find this kind of probabilities. So what we will do, we will say that probability of x comma y. So we have y values. Y values are fixed. So we can have multiple x values. So we can say x is equals to one sequence. So suppose sequence 1 given, not given because we're interested in joint probability, comma y is equals to given sequence. So given, I just say given sequence. Second can be probability of x is equals to sequence 2, comma y is equals to given sequence. So for all the sequence x can take, you obtain the joint probability, and then you can pick the maximum. So what I'm saying is, you see, suppose you have three states. So I'll erase this part also. Suppose you have three hidden states, 1, 2, and 3. And over here, this is y1, this is y2, and this is y3. Okay. So given this three sensor information, you are asking what is the real world? What is the values of, what is the what will be the real world situation? You are asking that. So what you do is you obtain, so, and suppose x can take three values. So how many sequences you will have? So for each you will have 3 times 3 times 3, right? So you'll have 27 sequences. X0 will take three values, x1 can take three values, x2 can take three values. So 3 times 3 times 3, you will have 27 such sequences. So you obtain 27 such joint distributions. Whichever has the highest probability, suppose this has the highest probability, then you can say given this information, I think that this is the situation of the world, because this situation has the highest probability. Is it all right? Or I should explain everything again? So what is the situation? Let us take one step back. I have a sensor which gives me y1, y2, y3. I am interested in the situation of the real world, right? So what I will do is I will take all possible combinations of the real world, x0, x1, x2. I have 27 such possible sequences. For all those 27 possible sequences, I will obtain the joint probability of x comma y, and whichever has the highest probability, I will assume that this is the real world situation with some probability. So I'll say that it is sunny, 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 sunny with 74% probability. My sensor is saying whatever it is saying, I think that it is sunny, sunny, sunny with 90% probability or 40% probability. So you see, this is happening in speech recognition as well. So you are speaking something to Siri or maybe Google Assistant or something like that. And what Google Assistant is having is actually a waveform. So it is having y1, y2, y3, some sequence of waveforms, right? It has a sequence of waveforms. What that assistant will do is, given that sequence of waveform, what maybe the person has spoken. So it will have different distributions, and then it will say, okay, I think that he has spoken something like this with 95% probability. Therefore, I will assume that he has spoken like this. So this is what it will do. Hidden Markov model, right? Am I making sense? Okay. Right. So such kind of questions you can answer. And you can divide it by probability of y, but since probability of y is a constant, you can just take the maximum of these 27, because probability of y is a constant. You know the probability of y from your sensor information. So you either divide it by probability of y or not divide it by probability of y, doesn't matter. You see, you had probability of x given y. This is what you wanted to know. This is probability of x comma y by probability of y. So probability of y is a constant. You just see what is the maximum of probability of x comma y, and then you can obtain. Okay. And here I have one more example of hidden Markov chain, and I'll just show you. Maybe. Okay, I should show you. What I have done over here is, okay, so over here what I have obtained, I'll show you the code, but over here what I have done is I have obtained this kind of probabilities. So over here I have obtained this kind of probabilities. So what is the probability of observed index, right? So what is the observed index? High, medium, low. So in this code which I have done, I have said y2 is equals to something, y1 is equals to something, and y0 is equals to something. So find this kind of probabilities. Over here in the code I'll show you just now. Over there I have obtained this kind of probabilities. What is the probability? y2, y1, y0 is equals to this. How you will do this? You will use the marginalization principle, or that conditioning law of total probability. You sum over all possible x's. You say probability of y2, y1 and y0 given x2, x1, x0 times probability of x2, x1, x0, and you sum over all possible x's, right? We explained this a little earlier. I hope you remember. We explained this a little earlier. So over here, this is the sample space. This is y, and these are x, different x. This is right. So we are saying what is the probability of this? You sum over all possible x's. Is that all right? I'll just show you the code now. That's why I'm saying. Any doubt? Okay. So whatever I have written over here, you can just read this. These are everything the same. So it is actually the same thing which I have told you. These are the references I have used. I'll just stop share from here. Yes.
Shubham, please let me see the references.
What differences?
Reference.
Okay. These slides will be with you. You can just.
Yeah, absolutely. Correct. Okay.
So for each of the slides which I have uploaded, every slide has a reference slide in the end. Okay. So you will find that in every slide. So my screen is visible or not? My screen is visible?
Yes.
Okay. So this is the hidden Markov model, which I have, you can say, assumed. There are three states of the world, hidden states: sunny, cloudy, and rainy. And this sensor has three kind of states. It can be high, medium, or low. And yeah, so some information of the, and this algorithm which I am using is just the thing which I have told you. Exhaustive search is actually, so you see, one thing I did not tell you is whatever we are doing is actually a computationally expensive task. For 27 sequences we obtain all those 27 sequences, and then we added all those, not added, multiplied, and then we compared. This is a costly thing to do, and that is what we are doing. Exhaustive search algorithm, this is actually an exhaustive search. So there are better algorithms to do the same thing, like dynamic programming. We have not talked about dynamic programming yet. If you want, then I can take dynamic programming later, but there are better algorithms to do the same. Since we are just learning the basics, then I am not going upon other algorithms to perform this kind of, this is actually a search problem, by the way. Among all possible sequences, which is the best sequence I have? These are all optimization problems, search problems. Am I right? You are getting it right. So you have 27 sequences, 27 possible sequences. Among these 27 possible sequences, the question is which sequence is the best? What is this? A search problem, an optimization problem. Each sequence has a cost, and you are trying to get that sequence which is, so like the maze problem. So the maze problem has multiple states, multiple sequences to go to the end, from the start state to the end state, and maybe each sequence has some cost. So you are trying to obtain that sequence which has the minimum cost, right? So these are all search problems. Currently we are doing exhaustive search. We are saying do everything, search everything, and then do the search problem, search. And in the next, from the next class, we will talk about optimization algorithms, where we will see that we don't need to, I'll not say don't need, where we'll what we'll do is we'll reduce the accuracy. We'll say कि चलो थोड़ा सा कम accuracy भी चलेगा, but do the search in less amount of time, something like that. Okay, so from the next class we will do optimization, how to perform search, and some approximations also. So how we'll do approximate algorithms and so on and so forth. So this is exhaustive search. Yeah, so the codes we need is iter tools and this numpy. So what is iter tools? It actually helps in permutation combination. So over here I have x1, x2, x3. I need all possible sequences, so that iter tools will help you obtain all possible sequences. Otherwise you have to run loops, one loop, two loop, three loop, and so on and so forth. Everything is built in this library. You can use this iter tools to obtain permutation and combination of things. Okay, so this is the states I have. These are the observable states. This is the transition diagram, and this is actually the conditional probability of the observable states. So given x, what is y? So this is the probability of that. So given x is equals to 0, so I have written over here. Actually it is not correctly written. Yeah, so this is O. Okay, so On is equals to j given xn is equals to I. Yeah, correctly written. Okay, this is what. Now these are the stationary distribution. So I told you we need a stationary distribution. Otherwise we'll not be able to say what is the probability of the start state, because that is where we start, right? And suppose we observe this sequence. So y0 is high, y1 is equals to medium, and y2 is equals to low. And over here we are just converting into the numbers. So we are saying this is 0, this is 1, and this is 2. Because these are strings and it is better to work with numbers, so we have just converted that into numbers over here. So this is the exhaustive search we are doing. We are passing the transition matrix, we are passing the probability matrix for the observable states, which is named as B. Pi is the stationary distribution, and this is actually the sequence in numbers. So OBS index is actually the sequence in numbers because it is better to work with numbers. So we have passed it into the exhaustive search. What it is doing, it is using iter tools to get all possible sequences. Okay, so it is doing that, and then for all possible sequences it is obtaining the probability and multiplying it, and then it is adding it. So we saw how we obtain probability of y1, y2, y3. You add for all x's. So for all x's, it is actually adding the probabilities and then returning the total probability. So I'll run it once and I'll show you. So given this transition probability matrix and this matrix for the observable state, the probability of seeing this observable state is actually this 0.3, 0.03. So this is the probability of observing this sequence, high, medium, low. Is it all right? Is it all right? So this is what I wanted to complete. I was hoping to complete it by 7:30, but it took a lot of time. I hope everything was clear. If it is not, please tell me. I'll try to improve. So maybe sometimes I feel I am not able to deliver very effectively. So I want some feedbacks from your end as well. All right, then I'll close today's class. One last announcement. So next class will be on Sunday, but I want to do one extra class in November because for the first 2 weeks of December I will take leave. I have to go somewhere, so two classes will not be there on the first and second week of December, and in that duration you will be asked to do the project. So please decide on what project you will do. I'll send a mail or maybe some announcement will be there in the Google Classroom on some topics, some suggested topics, and there will be a Google form or something like that I'll circulate to take from you the input, which the topic of your project. So I'll do that before the next class, and I have not prepared any assignment for this uncertainty that I'll try to release by tomorrow or maybe Tuesday, and I'll give you 7 days to upload the assignment, or deadline for the assignment will be 7 days from the time it has released. So that is all I wanted to tell you. I hope you are liking the course, enjoying the course. Okay, thank you. I'll end the meeting now.